Let's go ahead and talk about some of the benefits of object-oriented design. We'll be covering these benefits in much greater detail in Lesson 5 when we talk about the actual patterns and the pattern-oriented design and implementation of our expression tree processing app. But I want to give you a preview of coming attractions just so you're able to think clearly about what the benefits are of what we're doing. One of the benefits of an object-oriented design, especially in comparison with the original algorithmic decomposition we talked about in Lesson 3, is that the complexity resides in relatively stable structures and APIs, application programming interfaces, rather than in variable algorithms. Algorithms tend to change. You tend to have different ways of doing the functionality. You typically have new features that users want. But if you structure around something that's stable as opposed to something that changes, you're more likely to have a solution that will be able to evolve more readily and seamlessly and transparently over time. Another benefit of our object-oriented design is it has a much more faithful and accurate modeling of the expression tree design domain. Each node in our tree only contains state that's associated with that particular node. So we end up having a leaf node with no children. We have a unary node with one child. We have a binary node that has two children. And so as a general rule, compared to the algorithmic decomposition, where every node had the max for everything, we're able to keep things more succinct, more parsimonious. We only pay for what we're going to need at any given level of abstraction in our design. Another benefit is we have much better encapsulation. We're able to make it possible to replace implementations without changing the way the client code is going to work. We can change the implementation details in various ways without breaking commitments we've already made with existing client code. If you make changes to these implementation details, they don't ripple through the overall program implementation because they're encapsulated. We have effective use of access control specifications like public and private and protected and so on to make sure that you minimize dependencies and visibility across these different boundaries. Another nice thing about using an object-oriented design is it's very straightforward to add new capabilities in ways that plug in transparently based on the design that already is in place. For example, if we want to come along and add a new kind of node to our tree, let's say a ternary node, or we want to be able to add a new kind of modulus operator or something like that, it's very easy to add that to our existing design simply by inheriting from what's there and then filling it in within the existing confines of our stable application programming interface. There also, however, are some limitations with object-oriented design, and we have to be upfront about these because if you don't recognize them, you'll be caught by surprise and may end up spending a lot of time floundering around trying to deal with these limitations because you haven't properly scoped out the amount of effort required to build up the basis of tools and knowledge and other infrastructure to be able to succeed with this paradigm. One of the potential downsides of object-oriented design is you end up with many classes. You end up with many associated structures, and these structures are often related to each other in various subtle ways. And so if you don't have the knowledge and access to a good configuration management process and good configuration management tools, you'll end up with lots of files and lots of dependencies, and you'll end up drowning in a sea of details. Needless to say, there are all kinds of interesting and easy ways to get around this, but you do have to spend more time investing in the infrastructure than you would if you put everything into just a handful of files and dealt with it in a more macro level. Another potential problem, especially historically, with object-oriented design, there was some runtime overhead associated with the use of virtual method dispatching. Typically, a virtual method ends up having an indirection through what's called a v-pointer or some other kind of association between an object and a table of functions or methods that implement the interface for that particular object. And in the old days, there was some extra levels of indirection, looking up things into an array, chasing down pointers, and so on and so forth. And so you would notice a small amount of overhead relative to writing functions or inline code, which is more typical in an algorithmic decomposition. The good news is, after 20 years of effort developing and improving, optimizing object-oriented programming language compilers, the difference between a dispatch of virtual methods and a normal function dispatch is essentially negligible. There are ways of being able to optimize away the overhead. There's various use of things like adjuster thunks and other techniques for optimization of virtual method dispatching. And it's also important, of course, to realize that even a virtual function call is probably going to be roughly the same performance overhead as having a large switch statement or a chain of if-else sequences, even if you don't have the benefit of an optimizing compiler.